Okay, so I want to sort of conclude our journey into vectors in n space. Previously we've talked about the dot product, and also with that, if you recall, in 2 and 3 space we have this angle between the two vectors, and we can actually solve for that angle, and we can extend that to n space. The most important part of that, though, would be when the angle between two vectors in 2 and 3 space is 90 degrees or pi over 2, right? Then those two vectors are perpendicular to each other, or what we call orthogonal. And so we can extend that definition now to vectors in n space. Two vectors in n space are said to be orthogonal, which is perpendicular, but again, perpendicular usually is reserved for lines, orthogonal for vectors. It's the same thing though, if what? Their dot product is indeed 0. And so this is the way we can extend that, because we know in 2 and 3 space, if two vectors have a dot product of 0, then the angle between the two vectors is, again, 90 degrees or pi over 2 radians. That means the 0 vector must be orthogonal to every vector in n space, because anytime we take the 0 vector dotted with another vector, we will get 0. Also then recall, two vectors in n space are parallel to each other if what? One is a scalar multiple of the other. So we've got two concepts of vectors being orthogonal and being parallel. Now the 0 vector, remember, also is considered to be parallel to all vectors in n space, and so it's the one vector that's both orthogonal and parallel to every vector in n space. Kind of a weird thing, but that's again the uniqueness of the 0 vector. But let's play around with these ideas. So two important ideas: orthogonality that we've just talked about, and parallel. Let's find the value of k here that makes these two vectors orthogonal. So how would we do this? Of course, we're going to look at their dot product, right? Their dot product must be equal to 0. And so we learned last time, right, how to find the dot product from the component forms, and that's what we're going to do, right? So we multiply the first components of the two vectors together, and multiply the second components and the third components, and we add those all up, and these must be equal to 0. And so I have an equation in the variable k that I can solve for. So 6 minus 2, I get 4, plus a negative 4k or minus 4k equals 0, and I think we can all see that k must be equal to 1. So there's the value of k that will make these two vectors orthogonal to one another. Okay. Similarly, we can talk about two vectors being parallel. What is the value of k that will make these two vectors parallel? Okay. Well, what did we say about being parallel? They must be scalar multiples of each other. So there must be some scalar we'll say a. I don't want to use the same k because that's the unknown we're looking for in the third component of u. And that scalar a is used to say what? That u, for instance, is a scalar multiple of the vector v. So if they're parallel, this must be true. Okay. And so what I'm going to do is just look at this equation here, which says u, which is negative 2, 1k, must be equal to a times v, which if I scalar multiply by a, right, each of these components gets multiplied by a. And so two vectors are equal. These are both ordered triples, right? Vectors in 3 space. They're going to be equal if what? Their corresponding components are equal. So if negative 2 is 6a, if 1 is negative 3a, and if k is equal to negative 4a. Okay. Well, if I look at these first two equations, I can solve for a, can't I, right? Dividing by 6 here, I get negative 2 6, which is negative 1/3. And here, dividing by negative 3, I get negative 1/3. So both of these tell me that a is negative 1/3, and that has to remain the same for this last relationship. And so notice that I get that k is negative 4 times a, which is negative 1/3, and that gives me what? K must be negative times negative positive 4/3. So two important ideas, orthogonality and when two vectors are parallel. Some of you are either in Calculus 3 or have had Calculus 3, and you'll go into a little bit more with vectors. For instance, a non-zero vector n that's orthogonal to every vector in a line is called a normal vector for that line. So normal is another word that's used to define orthogonality, or perpendicularness, I guess. But usually that's reserved for the vector that's normal or orthogonal to every vector in a line. And then similarly, a non-zero vector n that's orthogonal to every vector in a plane is called a normal vector for that plane, and that's in 3 space. So in 2 and 3 space we have these ideas, and in Calculus 3 you talk about the parametric equations for lines and the equations for planes and so on. This can actually be extended to n space as well, but that's not what we're going to go into. So again, Calculus 3 will look at applications in this area, like finding the distance between planes or the distance between a point in a plane and so on. Okay, so we're not going to go in that direction, but we will look at one last thing, and that is the orthogonal projection. And so this is going to be important. In fact, we are going to define the formula for what's called the orthogonal projection of one vector onto another, and basically that proof, if you will, or that development will be the proof for our next test that you'll have to do. So you'll want to pay close attention here in a little bit when we derive that. So let's talk about this orthogonal projection. So given two vectors a and u whose initial points coincide at point Q, let's just use these two vectors here to do that. So the initial point is Q, and we'll let this be the vector u and this be the vector a. And we're going to drop a perpendicular line from the tip of u, the terminal point of u here, to a point P on the line parallel to and passing through a. So the vector a is parallel to and passing through this line. Let's draw the line that coincides, if you will, with the vector a. All right. So I'm going to drop a vertical line from that point. So it's going to be 90 degrees there. And that point that I get right there, we're calling that point P. Okay. And now we're going to construct a new vector, and we're calling it W1 right now, with initial point Q and terminal point P. So we're starting at Q and we're going to P. And so I'm going to draw a vector. I want to make it very clear that that's the right. And of course direction, right, from Q to P. So you have to have an arrow on that vector. You have to show the direction, right? So this vector is what we're calling the vector W1. Remember, this is a vector, so what do you need to do? Put an arrow over it, right? Anytime you have a vector from now on, the book will do it boldface, but we need to put arrows over those. And this vector is called the orthogonal projection of the vector u onto a. That's a big long name. This is the way it's typically denoted, PROJ for projection, but it's the orthogonal projection. Notice it's u and then a subscript a. So this is the projection of u onto a. Okay. Now, the vector w2, which is u minus w1, is called the vector component of u orthogonal to a. Let's construct that, and then we'll talk about it. So here is w1. What would u minus w1 be? That would be the same as u plus -1 times W1, right? Scalar multiple of -1. What is negative W1? It's just the same vector, but what, pointing in the opposite direction, going this way. And so if I add U to negative W1, that's U minus W1, I'm going to be over here, right, by that tip to tail addition method that we've talked about. Okay, so what I'm going to do is sort of draw a line perpendicular to this line I drew that is parallel to A. You might be thinking the X and Y axes, for instance, if we have indeed both, if this point Q is the origin. And then, so negative W1 is going to come across here, right? And we're going to hit right at this point right here. Of course, this again is 90 degrees. And there we have this vector here. That would be, and of course, going in this direction. This would be U minus W1. So this vector here is what we're calling vector W2. And that is the vector component of U orthogonal to A. So it's real important here. The orthogonal projection of U onto A is actually parallel to A. Parallel to A, right? It's collinear or parallel to A. So be careful. Orthogonal projection of U onto A. We're projecting, here's the orthogonal part, but it's actually, that vector is actually parallel to A. Now, W2, right, this has to be what? 90 degrees here. And so W2 is going to be orthogonal to A, and that's why it's called the vector component of U orthogonal to A. So notice this, I can do W1, slide W2 over, tip to tail approach. W1 plus W2 is obviously the vector U, and so U is the sum of these two vectors. We've decomposed U into the sum of two vectors, one of which is parallel to A and the other which is orthogonal to A. And note, since W1 is parallel to A, it must be a scalar multiple of A, right? In this case, notice the scalar multiple. Here's the vector A, here's the projection of U onto A, and therefore the value of that scalar multiple must be some value less than 1, because the length of the vector is shorter than the vector A length. They're pointing in the same direction though. Okay, before I define, give the formula, I want to look at a couple of examples where I just want you to be able to draw the projection of U onto A like I've done here. So things can change. What if I have here vector U and here vector A? Okay, what would the projection of U onto A look like here? Well, in doing this, what you're going to do, first of all, is take the paper and rotate. Rotate, rotate, rotate until that vector A is right on the horizon, is horizontal. And we're going to draw that line like we did before that's passing through A. So let's do that. Okay. And we want to then draw the perpendicular from the terminal point of the vector U to find the projection of U onto A. I want it to be perpendicular to this line, so I come down, and that's a 90-degree angle there. And now this is our point that we were calling P. Here's our point Q. We're going to draw a vector from Q to P, and that will be the projection of U onto A. I've drawn it now, so I'll rotate back the way we were. All right, so this vector here now is indeed the projection of U onto A. Okay. Notice in this case, again, it's parallel to A. It's a scalar multiple of A, therefore. Here's the vector A length here, and the projection of U onto A is now longer in length, so this time the value of K, if you will, the scalar that we're multiplying vector A by to get the projection of U onto A, is greater than 1, right? And so here it was less than 1, smaller. Here it was greater than 1. And then let's do one more. This time let's let this be the vector U and let this be the vector A. So draw the projection of u onto A now. Well, again, what do? We rotate. We draw that line that is parallel to A, passing through A. And then we draw from the tip of U a line perpendicular, 90 degrees there again, to that point right there. And now we're going to draw that vector from this common initial point of the two vectors, that point we're calling Q, to this point that we have. We call that point P. Right? And there it is. So there is the projection of U onto A. Okay, so notice again it parallel to A, but notice A is pointing in this direction, projection of U onto A is pointing in this direction. That means it's a scalar multiple. Projection of U onto A is a scalar multiple of A, but it's what that scalar multiple must be a negative number, right? So that's going in the opposite direction. Okay, so hopefully this idea is similar. A lot of you, if you've had physics and dealt with vectors in terms of force vectors, free body diagrams, things like that, you've drawn. You do decompose usually vectors into their x and y components, right? I mean, this is the idea of what we're doing here, into the x and y components. So it's important in that application. But we want to extend this to n space. So in other words, I can draw this in 2 space like I have it. Could probably even visualize it in 3 space, but what about 4 space and higher? We can't do this sort of thing there, so we need to find a formula to find this projection of U onto A. And so we're going to do it using this picture right here as motivation. So on the proof, then you would want to draw this diagram to start with. And label the vectors that are you're going to be using here. Okay, so using this, then we've got projection of U onto A. We're going to call W1 just so we don't have to write this out every time. But we're going to find a formula for this vector, for the projection of U onto A. In other words, given the vectors U and A, how can I find this projection of U onto A? Of course, W2 again we'll use is the vector that component that is orthogonal to A. So first of all, just make some notes. W1 again is the projection of U onto A. It is parallel to A, as we have said. So what does that mean? There is a scalar K, some scalar K, such that W1 is K times A. And we're looking for a formula for projection of U onto A for W1. And so I submit to you that we already know A. So the whole goal is just, what is that scalar? We'll find that scalar. You can see how the scalar is different, right? Less between 0 and 1, greater than 1, negative, and so on. But how do we actually find the actual value? Well, we're going to do that here. W2 we'll say is of course orthogonal to A. The vector component of U orthogonal to A. So that, what does that mean? Well, what we just learned, the dot product of W2 and A is indeed 0. Again, real important, arrows over vectors, scalar, no arrows over scalars. K and 0 are scalars. Okay, so here's how you start. We start with the fact that we know U is equal to the sum of these two, right? These are a way to decompose, if you will, U into 2 vectors, one parallel to and one orthogonal to the vector A. I'm now going to actually take the dot product of U with A on both sides, of course, and here we'll take W1 plus W2 dotted with A. And then over here on the right, I will use the distributive property we talked about for dot products. I can distribute the dot product over a sum of vectors. And it is important that you have that little dot between the vectors. If you don't, then that's confusing. You can't multiply vectors. We're doing a dot product of two vectors. So it is important to have that dot there. You can't just write them together. That's not multiplication. Well, first of all, right off the bat, let's just say W2 dot A we know is what? 0. So this goes away. That's 0. And then we have W1 dot A. Okay, so first of all, let's just recall the following. That A dot A is the magnitude of A squared. So we've used that relationship before, and we're going to use that here. So W1 we know is a scalar multiple, right? K times A. And so this whole thing here is just K A dot A by, again, a property of the dot product. So the K A dot A, I can pull that scalar out and just do K times the dot product of A with itself, but we know that's equal to the magnitude of A squared, and so we get that U dot A is equal to K times the magnitude of A squared, and I can solve for K now, which was our goal, and by dividing by the magnitude of A squared. Of course, that's so we are assuming then that A is a non-zero vector here. Okay, so these dot product scalar, this is a scalar, so there's our scalar quantity, and that's the value of K. And so let's answer the question, what's the formula? The projection of U onto A, that was the vector W1, as we've said, right? It's K times A, and we found K, so it's equal to U dot A over the magnitude of A squared times A. All right, so I don't put a dot there, right? This is a scalar multiple of A. So there's the formula. That's the answer. Of course, your proof will be to show all these things. And I think that's important, other than me just saying, here's the formula. Where'd that come from? Where'd all this complicated stuff come from? You kind of get a feel for where this can come from using these facts that we have. Okay, so that's the end of the proof. This is not part of the proof, but I just want you to see this, that I can write the projection of U onto A as this. Let me do it over here. I can write it as U dot A over the magnitude of A, and I've got two of them down here, right, squared, so I'm going to pull the other one and scalar multiply the vector A by 1 over the magnitude of A. So I'll write it that way. So this is 1 over the magnitude of A times A. So what do you know about this vector right here? This vector here is a unit vector, right? That's how we normalize a vector. Okay, but because of that, this scalar multiple, then that's the magnitude or the norm of the projection of U onto A. And so this tells me that the norm of the projection of U onto A is U dot A over the magnitude of A. So make sure you understand the difference between the actual vector, which has of course, not just the magnitude, but the direction as well, and it's given by this formula, and then this is just the magnitude of that vector is just this quantity. Okay, so again, that's not part of the proof. It's just a little extra, right, to talk about. Okay, so that's what you'll need to do on the test. I just want to quickly close with one last thing. As we're talking about orthogonality, very important theorem that we use, I'd like to extend that to n space, and that's the Pythagorean Theorem. And it says if U and V are orthogonal vectors in n space with the Euclidean inner product, that's the dot product, then we have this relationship. Okay, why is this the Pythagorean theorem? Well, if we draw these vectors, let's say in 2 space, if this is vector U, right, then vector V being orthogonal, I can draw vector V in this way, 90 degrees right here, right, vector V, and then U plus V would be what? This corresponding vector here. And you see we have this right triangle, the hypotenuse being the norm of u plus v, so the hypotenuse squared is equal to the sum of the squares of the other two sides. And so it makes sense. The proof is pretty quick. I can't draw a picture like that to prove it because we're talking about n space or higher, but I will use the fact that the norm of a vector squared, right, norm of a vector squared is just the dot product of the vector with itself. So I'm going to just use that again. We use that idea quite a bit. And I'm going to use the distributive property of dot product over a vector this way first of all. So this is u plus v dotted with u plus u plus v dotted with v. And then I'm going to use the distributive property this way. You might say we're foiling in a sense, but again, it's not quite. That's not multiplication. So we do want to do this carefully. Okay. And so what do we have here? Well, u dot u, going back to what we just went this way, this is the same as the magnitude of u squared. And v dot v is the magnitude of v squared. Now you might say, what about these two? What happened to those two? Well, what do we know about the dot product of u and v? Well, remember, we're assuming what? U and v are orthogonal, right? And if that's the case, both of these dot products are 0. And so we have indeed proved this theorem for the Pythagorean theorem in n space. Okay, so that's the end of our discussion on vectors, and we are going to be in the next journey. We'll be getting into chapter 4 in the book, and we'll be looking at vector spaces, which will be lots of fun and excitement. It'll be a little different though, and so looking forward to it.